okay, which is a module 6. So this module 6 is actually one of the data processing in which you are going to do the data shifting, and sometimes you're going to do some data rotation. So there are few instructions that involve data shifting and data rotation. Okay, one of them called as a LSL. Okay, so the LSL stand for logical shift left. All right, so this logical shift left instruction shift all bit in RD one place to the left. Okay, and then bit 0 is a clear, and bit 7 is loaded into the C flag of the status register. Okay, so this is your registers. Okay, so the register is 8-bit size or 8-bit wide. Okay, you have a bit 0 and bit 7 here. Okay, so what happens when you do the LSL? All right, so 0 from outside, okay, value 0 from outside will go to your bit 0. And then what happens after that? Okay, this bit here, bit 0 will be shifted to the left, which is it will be shifted to bit 1 by 1 bit. Okay, and then bit 1 will go to the bit 2 goes to bit 3, and it will, all the bits here will be shifted by 1 bit. And what happened to your bit 7? So the value inside of the bit 7 will go to your C flags. Okay, so this is the operation for LSL. Okay, so this is the operation and this is the syntax. Okay, LSLRD, in which your RD can be from R0 to R31. And whenever you do the logical shift left, whenever you execute the LSL, what happens here is you effectively multiply signed and unsigned value by 2. Okay, means that after you perform the LSL instruction, it automatically, okay, multiply the value of the register, whether it's an unsigned number or signed number, by 2. Okay, so I think let's look at examples here. Okay, we have a few examples so that you can see very clearly how this data shifting and data rotation works. Okay, let me open the whiteboard. Okay, can you see this screen here? Okay, so you have L. Okay, sorry, not this one. Okay, so L. So you have LDI R16 0x33. Okay, so this is the value that you're going to put to your R16. And then next, what you're going to do here is you're going to do LSL. Okay, so your LSL R16. Okay, now we're going to find out what is the value, okay, inside R16 after you perform the logical shift left. Okay, so before that, so this is your LSL. Okay, so the LSL says that, okay, so this is the operation. 0 from outside will go to your bit 0. Okay, while bit 7 here will go to your C flags. Okay, and then the rest will be shifted to the left by 1 bit. Okay, so since this one here, this is a R16 OX33. So what you're going to do here is, okay, so we need to change this hexadecimal to binary representation, okay, to binary numbers. Okay, so 33 change to binary, you will get 0011 0011. Okay, then by using this operation here, which is 0 from outside, okay, we'll go to bit 0, and then the rest will be shifted to the left by 1 bit, and this one will go to your C flag. So what happened here is you just replace, okay, put the 0 to your bit 0, and then 1 will be shifted to the left. Okay, this one also will be shifted to another to the second bit, and the rest will be shifted to the left by 1 bit. Okay, so what about this 0 here? So this 0 here will go to the carry flags. Okay, then what you're going to do? Okay, you need to find out what is the answers here. Okay, the hexadecimal representation after you done the shifting. Okay, the LSL shifting. So here you will get R16 equal to, okay, so this one here is 6. Okay, so 6. Okay, previously we already it already stated that for the for the LSL, okay, it's actually multiply the value of your register by 2. Okay, so previously, okay, R16 is 33, and then when you multiply by 2, you will get 66, which is this is approved by using the same operation lah. Okay, so that's why it's for the LSL. Okay, next so this is the example. So I already show you the example, so I just skip this example here. And then we have the LSR. So LSR stand for logical shift, right? So this instruction shift all bits in RD in your destination register 1 place to the right. Meanwhile, the bit 7 is cleared and bit 0 is loaded to the C flag of the status register. Okay, so you as LSR, what LSR do? Okay, 0 from outside will go to your bit 7, and bit 0 here after you shifting will go to your C flag, and the rest of the bit will be shifted to the right by 1 bit. Okay, and then you see here, so by using this operation, effectively divided an unsigned value by 2. Okay, so if you use this LSR, actually it is divided unsigned value by 2. Okay, so let's look at the examples. Okay, previously we do the LSL. Okay, this instruction here is executed sequentially. So now you have the LSR R16. So what happened for the LSR? Okay, so this is your LSR. Okay, so this is the operation here. You have 0 from outside go to your bit 7. Okay, while this bit 0 here will go to your C flags. Okay, and then the rest of the bit will be shifted to the right by 1 bit. Okay, so the previous value of R16 is 66. Okay, so now this is the previous value. Okay, so now you do the LSR. So what happened here is, okay, 0 from the outside go to your bit 7. So this is your bit 7. You get 0. And then this one here will be shifted to the right by 1 bit. So the rest of the bit you shifted to the right by 1 bit. And what about this 0 here? So this 0 will go to your carry flags. Okay, and then let's find out what is the result. Okay, what is your current value of R16? So your R16 now become 33. Okay, so R16 equal to 33. And previously, okay, for the LSR, it stated that by using the LSR, is actually you divided your value, okay, your registered content by 2. This is only valid for unsigned numbers. Okay, so since this is an unsigned number, so you divided 66, okay, you divided by 2, then you get 33. Okay, so this is for the LSR, okay, logical shift right. Then we have another instruction called ASR, okay, which is arithmetic shift right. So the ASR instruction shift all bit in the destination register one place to the right, okay, and meanwhile the bit 7 is held constant, okay, means you copy back your bit 7 and bit 0 is loaded to the C flag of the status register. All right, so this is the operation for ASR. Okay, you have a 8-bit data, 0 and 7. Okay, so this bit 7 here, you copy back the number. Okay, the number will remain at the bit 7. And next, the other bits will be shifted to the right by 1 bit. What about bit 0? Bit 0 will go to your C flags. Okay, and then by using this operation, it actually effectively divides sign value by 2 without changing its sign. Okay, means that by using this instruction, you're going to divide the content of the register by 2, and it is valid for sign number. Okay, because previously, okay, for the data process in the arithmetic operation, we doesn't have division process. Okay, we doesn't have the division operation. So how to do the division? Okay, by using this shifting instruction. Okay, either you're going to use the LSR or ASR. Okay, depending on the numbers that you use, either is a signed number or unsigned number. If it's unsigned number, then you can go to by using the LSR. If the number is a signed number, then you need to use the ASR instruction. Okay, so let's look at example here. Okay, then next we have the ASR R16. Okay, so what the ASR do? So this is your ASR. Okay, actually, okay, you have 7, 0. So bit 7, you copy back the bit, okay, the value, and then you shift to the right by 1 bit, while 0 will go to your C flag. Okay, so the current value of R16 is 33. Okay, so now what you're going to do is you need to copy bit 7 to bit 7. So you copy this one to here. Okay, and then you shift to the right by 1 bit. So this one becomes 0, 0, 1, 1, 0, 0, 1. What about this one? This one will go to your C flags. And let's find out what is the value here. So you will get 1, 9. Okay, so R16 now equal to 1, 9. Okay, so actually this one you're going to divide it by 2. Is it correct? 33. Okay, press the calculator. Is it you? Okay, you press the calculator, and what is the result you get? Okay, 33 bahagi 2, and then you get 1, 9. So betul lah. Okay, so the answer is correct. Okay, next we have next instruction. Okay, ROL. Okay, so ROL stand for rotate left through carry. Okay, so this instruction shift all bit in destination register one place to the left. Okay, means that you shift all the bits to the left by one bit. And then the C flag is shifted to bit 0 of RD, and bit 7 is shifted into the C flag. Okay, so this is what the ROL do, the rotate left. Okay, so you have a 0, 7. Okay, now you have two C flags. Okay, one I call it as a C old, and the second one we call it as a C new. Okay, so what happened here is, okay, so the C old will go to your bit 0, and then after that you shift all the bit to the left by one bit. And what about bit 7? The bit 7 will goes to your C new. Okay, so you have a new carry depending on the bit 7 here. Either the bit 7 is 0 or 1. Okay, so this operation, when you combine with LSL, effectively multi-byte signed and unsigned value by 2. Okay, if you're going to do the to multiply 16-bit number, okay, you can use the if you're going to multiply 16-bit number by 2, so you can use the LSI, and after that ROL, so that you can do the multi-byte by 2. Okay, because it is a 16-bit number, so for the 16-bit number is actually a multi-byte, so you can combine LSL and ROL to multiply that 16-bit number by 2. Okay, so let's look at examples. Okay, again, now we have the ROL R16. Okay, so what the ROL do? So ROL, okay, so this is your C old. Okay, we go to your bit 0, and bit 7 we go to your C new. Okay, so from the previous instruction, okay, your R16 is 19. What about your C old? What is your C old value? Anyone? Can you tell me what is the current or the C old value, the current C flex? Okay, 1. Okay, so here, this is your C old actually. Okay, the C produced after you execute the ASR instruction. Okay, so what happened here? This C here, okay, so this is your C old, will go to your bit 0. Okay, here we'll go to here. What about this one? Bit 0, bit 0 will be shifted to the left by one bit, and the rest will follow. What about this one? Okay, and this one here will go to your new C. Okay, so this is your C new. Okay, and then what is the result? The result is 33. So R16 now equal to 33. So actually 90 you multiply by 2, you will get 33. Okay, so this is for the ROL. And then next, okay, we have the ROR. Okay, so ROR stands for rotate right through a carry. So this ROR instruction shift all bits in RD one place to the right. Okay, means that all the data in the register will be shifted to the right by one bit. And the C flag is shifted to the bit 7, while bit 0 is shifted into the C flag. So again, for this ROR, you have two C. Okay, you have two C flag. One is a C old, and the second one is C new. So these are ROR, and this is your registers 0 and 7. Okay, then what happened here? You have two C here. One is old, and the other one is C new. So what happened? C old will go to your bit 7, and then the rest of the bit will be shifted to the right by 1 bit, while bit 0 will go to your C new. Okay, and this operation, when you combine with ASR, effectively divide multi-byte signed and unsigned value by 2. Okay, if you're going to divide it 16-bit number by 2, you can combine ASR with ROR to do that. Okay, and then we look at the what we call here examples here. Okay, next we have the ROR R16. So what happened? ROR. Okay, so this is the operation for ROR. Okay, C all go to bit 7, and this one will be shifted to the right by 1 bit, and bit 0 will go to your C new. Okay, so the current value of R16 is 33. What about your C? C all, what is your current C value? Okay, previously the C is 0. Okay, you see here, the C is 0. So this C here will go to your bit 7, and the rest of this bit will be shifted to the right by 1 bit. Okay. Okay, what about this one here? This one will go become your C new. Okay, and what the result? Okay, so the result after you perform the ROR is 1, 9. So R16 equal to 1, 9, which is you're going to divide it the 33 by 2, then you will get 1, 9. Okay, so this is another example. Okay, you can do it yourself. Okay, see how it works. Okay, next we have the B set. Okay, so this B set stand for bit set in status register. Okay, so the bit set instruction tells the CPU to set a single flag or a bit in status register. Okay, means that sometimes you're going to set your flag register. So how to do that? You can use the bit set instruction. So what is the operation of the bit set? Okay, so here you see here, okay, you put 1 to your status register, okay, depending on the bit that you are choose. Okay, so this is the syntax bit set as. S is actually the bit location. Okay, starting from bit 0 until bit 7. Okay, for example, okay, you're going to set your C so that your C equal to 1. So how to make your C equal to 1? Okay, you can use the bit set. Okay, so by referring to the status register, so this is your status register. Below here is your status register. Then you need to identify lah. Okay, your C flag at what bit? Okay, so you put D is 0, 1, 2, 3, 4, 5, 6, and 7. Okay, now you're going to set your C flag. So what you're going to do is you just use the bit set 0. Okay, why 0? Because your C flag, okay, at bit 0 inside of your status register. So after you execute this instruction, what happens? C automatically become 1. Okay, so this is what the bit set do. Okay, for another example, okay, you're going to enable your interrupt, okay, flags I, so that it become 1. So how to do that? Okay, to do that, you can use the bit set instruction, bit set, and what number that you're going to put here? Okay, for I, it is a bit 7. Okay, the location of I inside of status register is at bit 7. So you just simply put bit set 7. So what happened? I equal to 1. Okay, this is for the bit set. And then we have another instruction called a bit BCLR, means that you're going to clear the bit in status register. Okay, so the BCLR instruction clear a single flag or a bit in status register. So this is the operation. Put 0 to your location that are pointed by S, okay, to the bit that are pointed by S inside of your status register. Okay, so this is the syntax. BCLR S, in which S is your bit location starting from bit 0 to bit 7. Okay, now you're going to clear your V flags. Oh, sorry. Okay, so you're going to make your V flag equal to 0. So how to do that? Okay, you just simply write BCLR and identify what is the location of V. Okay, so this is 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so V is a bit 3, so you just simply put BCLR3. So what happens after you execute this line? Your V automatically equal to 0. Okay, if you're going to disable your interrupt flags, what you're going to do? Okay, so disable interrupt flag means that you're going to put I equal to 0. Okay, so you just use the BCLR7. So what happens after you execute this line? Your I now equal to 0. Okay, your I flag is cleared. Okay, which is you put 0 to that I flags. Okay, any question up until here? Ada soalan tak? Okay, if no question, okay, then next we go to the next instruction. Okay, we have the next instruction is a BST. Okay, so this BST actually stand for bit store from bit in register to deflect in status register. Okay, so what this BST do? This BST store bit B from your destination register to the T flag inside of your status register. Means that, okay, you take the value from your destination register, okay, any bit, okay, any value either is 0 or 1, and put it to your T flags. Okay, so this is an operation. Okay, get the bit, the value from the bit inside of your destination register and put it to your T flags. So this is the syntax BST RDB. Okay, so if you're looking at this status register, only T flags affected. Okay, other flags remains unchanged. Okay, so for example, okay, I put some examples here. R17, okay, you have a R17 value such 1011 0110. Okay, then I use the BST R17 2. So what happened here? Can you tell me what happened here? Okay, the R17, okay, have a value 1011 0110, and then next I do the instruction BST R17 2. Okay, so what happened after you execute this line?
T flag become 1.
Okay, so T flag become 1. Is it a T flag become 1? Okay, so you need to check. Okay, so this is your R17. Okay, so this is your R17. Okay, and then you put the bits lah. Okay, for this, each of these numbers here. So this is a bit 0, bit 1, 2, 3, 4, 5, 6, 7. Okay, so what happened here when you do the BST R72 means that you go to the bit 2 inside of your R17. Okay, so this is a bit 2 inside of your R17. Takes the value and put it to your T flag. So automatically your T flag equal to 1. Okay, let's say another instruction, BST R17 6. So what is your T value after you execute this instruction here?
Zero.
Okay, your T become 0. Why become 0? Because you go to your bit 6 inside of your R17. So this is your bit 6 inside of your R17. Takes the value and put it to your T flag. So automatically your T flag equal 0. Okay, next we have the BLD. Okay, so the BLD stand for bit load from T flag in the status register to a bit in register. Okay, so please change this one here. BLD. Okay, so this BLD instruction copy your T flags. Okay, so whatever your T flags value, you copy that value and put it to your register in the specific bits. Okay, so this is the operation here. Okay, take the value of T and put it to the bit location inside of your register, destination register. So this is the syntax BLD, RD, and B, in which RD can be from R0 to R31, while B is from bit 0 to bit 7. Okay, let's okay, you have another, okay, so this one here, we takes R20 equal to 10, 11, 0, 1, 1, 0, for example. Okay, so this is your R20 value. Okay, then I just use the B. Okay, and then followed by BLD. Okay, R23. Okay, so what happened here? Okay, you have two instructions here. Okay, the first instruction, what the first instruction do? Anyone?
Copy the value to T flag.
This is B set. B set seed. What is the meaning of B set seed? Okay, see here. This is a B set. Okay, B set 6. What are you going to do?
C
In this
equals to
instruction.
1.
Okay, you go to the location of 6 inside of your status register and make it as a 1. Okay, so this is a 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so 6 is actually your T flag. Okay, so now what happened here is you make your T equal to 1. Okay, then BLD R23. Okay, what happened here?
Copy the T flag to bit 3.
Okay, you copy the T flag value, which is 1, and put it to your bit 3 in the R20. So this is your R20. This is the initial value of R20. Okay, you go to bit 3. So this is your bit 3. Okay, so this is your bit 3. Now, what happened here is you copy the T value. Okay, load the T value, which is 1, to the location of R20, okay, to the bit 3 of R20. So now your bit 3 R20 equal to 1. So what happened to R20? So R20 now will have a new value lah. Okay, previously, okay, the initial value of R20 is 8421 and this is 8421. Okay, the initial value of R20 is B6. Okay, but because of you doing the, okay, you execute the BLD R23, so what happened now? Your R20 become, okay, so this is 8 plus 2 plus 4 is 14, and now it become BE. Okay, you see here? Okay, next I add another example here. So BCLR 6 and BLT R27. Okay, so what happened? In line number 3, okay, for the instruction number 3, what this instruction do?
Clear the T flag.
Okay, you clear your T flags. Okay, then for the line instruction 4, okay, you're going to load the value of your T flag to bit 7 inside your R20. Okay, so now our current value of R20 is 10111110. Okay, so this is the bit 7. Okay, you go to the bit 7 and now you load the T value, which is 0 to your bit 7. So what happened to your R20? R20 will have a new value, which is 3E. Okay, so this is what the BLD and BST do. Okay, next we have the SEC. Okay, so SEC stands for set carry flags. Okay, whenever you're going to set a carry flag, you can use the SEC. Okay, so the SEC instruction set the carry flags, which is your C flag in your status register. So this is the operation. Put 1 to your C flag. The syntax SEC operands none. Okay, so you see here only C flags affected, which is a C always 1. Okay, so if you're going to set your carry flag, so you just simply write down SEC. Or if you're not going to use this instruction here, okay, you can use the B set 0. Okay, which is this is also equivalent lah. Okay, do the same thing. Okay, you're going to make your C flag or your carry flag as 1. Okay, you're going to set your carry flag as 1. Okay, then we have the CLC. Okay, so the CLC means you're going to clear your carry flag. So every time you use the CLC means that you're going to put 0 to your C flags. Okay, your carry flag. So this is the syntax CLC. So if you're going to clear your carry flag, you just simply use the CLC instruction, or okay, you can do another instruction which is a BCLR instruction, but you need to know the location of your C flag. Okay, and then this is the flag affected. Okay, the C flag will always 0 after you execute this instruction here. Okay, then we have the SEN. Okay, so the SEN stand for set negative flags. Okay, you're going to make your N flag equal to 1. So by using, you just simply use the SEN. Or if you don't want to use the SEN, you can use the bit set instruction as well. Okay, which is you need to put one number here so that your N flag equal to 1. For the bit set, what bit that you're going to put here? What number you're going to put here so that you will set the N flag?
2.
0, 1, 2. Okay, so you just use the bit set 2, which is equivalent to SEN. Okay, then if you're going to clear your N flag, you can simply use the CLN instruction. Okay, so CLN, okay, equivalent to BCLR2, which is you're going to make your N flag 0. Okay, so that's why if you see here, okay, only N flag is affected, which is the N flag always 0 every time you use the CLN instruction. Okay, then we have the to set the 0 flag, you can use the SEZ. And if you're going to clear your 0 flag, you can simply use the CLZ. Okay, and last but not least, okay, this is the most important thing, okay, because you always use this one here for interrupt programming. Okay, so every time you're going to do the interrupt programming, you need to enable your I flag. So how to enable your I flag? By using the SEI instruction. So means that every time you put the SEI, you execute the SEI instruction, what happen here? Your I flag automatically become 1. Or if you're not going to use the SEI instruction, you can use another instruction called the bit set. And please make sure that the location of your I flag is correct, which is bit set 7. Okay, so automatically I equal to 1. Okay, you see here, I always 1 every time you use execute the SEI instruction. Okay, next, if you're going to disable your interrupt flag, so how to do that? Okay, you can clear it by using the CLI instruction. Okay, so CLI stands for clear global interrupt flag. Okay, so every time you execute this instruction here, what happens? Your I flag equal to 0 means that you disable your interrupt programming. Okay, or you can simply use the BCLR 7, which is it. Okay, so this instruction also do the same function, which is you're going to make your I flag equal to 0. So any question up until here? Okay, we finished our module 6 actually. Ada soalan tak? Do you have any questions? Okay, if no questions, okay, then I think, okay, we can do this exercise here. Okay, so this one here, okay. Okay, I will get a new one because this one here already been blurred by this instruction sets. Okay, so let me get the new one here. Okay, so I will give you, okay, 10 minutes, okay, and you need to figure out what are the value of each of these registers here after you execute each of these instruction. Okay, so make sure that the answers, your answer must be in hexadecimal. Okay, and these instructions are executed sequentially. Okay, so this question is taken from previous test, if not mistaken. Okay, so this question is 12 mark. Okay, I give you 10 minutes and you do. Okay, so let's look at the first instruction. Okay, the first line here. Okay, load I R2016. Okay, so what would be the R20 value?
10.
10, Doctor.
10. Okay, so first, what you're going to do here is you need to identify what is the number system for this value. Okay, since this one here doesn't have any symbol in front of the numbers, so you know that, okay, this value here is a decimal number. So since this is a decimal number, so what you're going to do is you need to change, okay, 1/6 decimal to hexadecimal. Why? Because the R20, all the value, all the destination register must be in hexadecimal number. Okay, even though you put 1/6 here, then the answer will be wrong lah, because this one must be in hexadecimal. Okay, so 1/6 you change to hexadecimal, then you will get 1, 0. Okay, what about the second instruction? LDI R21 0B10101010. So what would be your R21 value?
AA.
Okay, so this one is AA. And then number 3, SEC. So what the SEC instruction do?
Set carry flag.
Okay, you're going to set your carry flags. So your carry flags become 1. And then, okay, line 4, ADC R20 R21. Okay, so what this ADC do? You're going to add, okay, R20 equal to R20 plus R21 and plus with C. So this is what the ADC do lah. Okay, add R20 plus with R21 and plus with C. So R20 is 10, R21 is AA, and plus with C, what is your C? The C is 1. Okay, the current value of your C is 1. Okay, so that's why plus with 1, then you will get, berapa dapat kat situ? 10 plus AA plus with 1, then you will get BB. Okay, so BB. Okay, so what you're going to write down here? So R20 equal to BB. What about R21? What is the value of R21?
AA.
Okay, remains no change, AA. And what would be your C flags?
0.
Okay, your C flag equal to 0. Why 0? Because after you do the addition, okay, there is no carry from bit 7 to bit 8. So the C flag equal to 0. Okay, and then number 5, ASR R20. So you need to know lah what the ASR do. Okay, so recall back, this is what the ASR do. Okay, you're going to copy bit 7. Okay, the value of the bit 7 to bit 7, and then the rest of the bit you shift to the right by 1 bit, and this one will go to your C flag. Okay, since your R20, okay, your R20 is a BB, okay, so you need to change the BB to binary numbers. Okay, so change this BB to binary number, you will get 8421, 8421, which is BB is actually 11. B is 11, so 1011, 1011, and then you do the ASR. Okay, so this is a 1, 1, 0, 1, 1, 1, 0, 1, and 1 to your C flag. Okay, and then you change back to hexadecimal. Then what is your answers here? Okay, so what is the answer of R20 after you do the ASR?
DD.
Okay, DD. Okay, so C flag no need to put lah, because this one here, okay, the C flag, okay, doesn't have a blanks here, so no need to put the C flag. Okay, by right, the C flag is 1 lah after you did perform the operation. Okay, the instruction. Okay, then line 6. Okay, instruction 6. MOVW R22 R20. Okay, so what does MOVW do?
Move between
the word.
Okay, you're going to move one word, okay, one register pair to another register pair. Okay, since this one here, you're going to move word, okay, or 2 byte of data from R22, okay, sorry, R20 and R21 to R22 and R23. Okay, so you're going to copy R20, R21. So 2021 is actually DDAA. You're going to copy this value here, one register pair value, okay, or 16-bit numbers to another, to one pair of register, which is R22, R23. Then it becomes DDAA. Okay, so this is the answers. And then after that, number 7, okay, instruction number 7, SBR R23OX5. Okay, what this instruction do? Okay, you're going to set bit, okay, your register with this value here. Okay, your current register R23 value is AA. So AA actually is 1010, 1010, and then you're going to do, okay, if you refer to what we call here instruction set summary, okay, this SBR actually do this thing here. Okay, SBR, you're going to set bit in register, okay, and this is the operation, okay, which is you're going to do the logical OR with the immediate value of K, okay, and then put the result to your RD. Okay, so your RD is R23, and then your K is actually 5. Okay, so you change this 05 to binary number, then you will get 00000101. Okay, and then you do the logical OR. Okay, when you do the logical OR, you need to refer to the truth table or truth table. Okay, and then you compare bit by bit. So 0 or with 1, you get 1 is a 1, 1, 1, 0, 1, 0, 1. Okay, and then you change it to the hexadecimal, you will get AF. Okay, so the answer here will be AF. Okay, any question up until here?
Yes, doctor.
Okay.
How did
Yeah.
you how or why did you copy R21 to R23? But it's not stated on the instruction, on the parent and instruction.
Okay, so MOVW, this one here, this instruction. Okay, if you will refer back to what we call here instruction set. Okay, I already upload the instruction set in your e-learning. Okay, you can download them from the e-learning. Okay, so we go to this instruction set. Okay, and then we go to MOVW instruction. Where is my MOVW instruction?
Up.
At the top. Okay, ADD. This one doesn't have. Okay, okay, this one. Okay, you see MOVW RDRR, which is you're going to copy register pair. Okay, RD plus 1 RD, RR plus 1 RR. So now your RD is R22 and RR is R20. So what happened here, if you put it inside of this operation here, so it's meaning that R20, R21, you're going to copy this value here to R22 R23. Okay? Did
Okay.
you answer your question?
Okay. Okay.
Okay. So you need to refer to this what we call here instruction set. If you confuse what the instruction do, so you can refer to the instruction set and go to this column here. Okay, the operation column, so you can know what exactly this instruction do.
Okay.
Okay, next we have the line set. Line 8. Okay, so the line 8 here, you're going to instruction 8 is ANDI R20150. Okay, so what the ANDI instruction do? Okay, you're going to do the logical AND. Okay, between R22 with an immediate data 150. So R22, what is the current value of R22? Okay, you have a DD here. Okay, so R22 is DD. So DD is 1101 and 1101. So this is your DD. And then you're going to end with 150. Okay, since this is 150 is decimal number, then you need to convert to binary lah. Okay, so 150 convert to binary, you can simply press your calculator, then you will get 1001 and 0110. Is it? Betul tak? 96. Okay, correct. Okay, so this is a 105. Okay, and what you're going to do? You're going to do the logical AND. So by referring to the AND truth table, then you compare bit by bit. Okay, so 10, you will get 0. 0 and with 1, you get 0. 1 and with 1, you get 1. So this one also 0. 1, 1, you get 1. Okay, so 0, 0 is 0. 1, 0 is 0. And 1, 1 is 1. So the final answer will be 9, 1, 2, 4. Okay, 9, 4. Okay, anyone get the same results for line 8?
Yes, doctor.
Okay, and last but not least, swap. Okay, so swap means that you're going to swap the position. Okay, from low neighbor go to high neighbor and high neighbor go to low neighbor. Okay, so now the value of R22 is 94. So what happened here is 4 will go to location 9 and 9 will go to location 4. So the final answer will be 4,
9.
9. Okay, any question up until here? Okay, if no question, okay, we're going to have another examples here. Okay, another what we call here exercise. Okay, I will give you another 10 minutes, okay, to solve this exercise here, and then after that we discuss the answers. Okay, so sekejap ya, I copy the question first. Okay, can you see this one? Semua nampak ya?
Yes, doctor.
Okay, so I give you 10 minutes, and then after that we discuss the answers. Part. Okay, for the first line here, okay, you have the LSL R20. Okay, so first line. So what would be the answer here? R20?
I think 79.
79. Okay, some of your
Think.
friends saying that 79. Other than that?
E6.
Okay, we get a E6.
E6, doctor.
Okay, and then anything other than these two answers here? Okay, so let's check. for the first instruction here. Okay, we have two answers here. One is a 7, 9, and the second one is E6. Okay, so you're going to do the logical shift left. Okay, so logical shift left, if you recall back, okay, so this is your registers. Okay, so what happened when you do the LSL is actually you're going to put 0, okay, to your bit, what you call here, bit 0. And then after that, all this bit here will be shifted to the left by 1 bit, and bit 7 here will go to your C flat. Okay, and now R20, what is would be the R20? R20 is F3. Okay, you change this F3 to binary representation first. Okay, so F3 is F11110011. Okay, and then what you're going to do here is by using the LSL. Okay, so put 0 to the first bit. Okay, the bit 0, and then the rest will be shifted to the left by 1 bit. So you will get, okay, and then what about this one? This one will go to your C flat. Okay, and once you finish, then you change it to hexadecimal. So the hexadecimal is by using the add 4 to 1 method. Okay, you will get 8 plus 2 plus 4 is actually a 14. Yes, 14. 14, you convert it, it is actually as E. And then this is a 4 plus 2, you get 6. So the correct answer is E6. Okay, so this kind of question, make sure that you need to make sure that all the answer will be correct lah. Why? Because if your first answer is wrong, then the following answer might be wrong. Okay, why? Because it is executed sequentially. Okay, so this is very crucial lah. The first part here is very crucial. Okay, next, the second instruction here, ANDI R2155. Okay, so what you're going to do here is you're going to AND R21, which is FD with value 55. So you have FD. Okay, so I've just put down here. FD convert to binary, you get 1111. And D, what is a D? A, B, C, D. D is a 13. 13 is 1101. So this is a FD. And then you're going to do a logical AND with 5. Okay, so 0, 1, 0, 1, 0, 1, 0, 1. Okay, and then you do the logical. Okay, so what would be the value here? Okay, what is the result? So this is 1, 0, 1, 0, 1, 0, 1, 0. So you will get 5, 5. Okay, so make sure that all the answer must be in hexadecimal lah. Okay, because the register, okay, the data memory is in hexadecimal. Okay, all of you get 55?
Yes.
Okay, and then, okay, before that, okay, so this LSL is actually multiply by 2. Okay, this LSL is actually, you're going to multiply your register value by 2. Okay, since our value is F3, so F3, if you multiply by 2, you will get what would be the answer here? You press the calculator. F3 multiply by 2, you will get 1 E6. Is it correct? Betul tak? You will get this answer. Okay, if you put the 1 E6 here there, then the answer will be wrong lah. Okay, why wrong? Because this one here, you see, this is greater than 8-bit. You have a 12-bit here or 16-bit. So what you're going to do, you need to divide it by 2. 1 is a low and 1 is a high byte. So the low byte you put to your R20, while the high byte you just ignore it. Okay, so the answer is E6. If you put 1 E6, then it is incorrect. Okay, then next we go to instruction number 3. Okay, NEG R20. So what the NEG do? What
Flip.
the, okay, 2 complements.
Second
You're going
complement.
to do the 2 complements. So R20, what is the current R20? E6. Okay, so this is your current R20 E6. How to do a 2 complement? Okay, from traverse from left to the right. Okay, so this is a E6 traverse from left to the right. You need to find the first one. Okay, so this is your first one. And what you're going to do? Okay, you copy back the value. Okay, 1, 0. What about the rest? The rest you just simply invert them. Okay, so kamu akan dapat, you will get the answer will be equal to 1, 8 plus 2 is 10, 1, 8. Okay, so this is a 1, 8. Or you can simply press the calculator, okay, by looking at the what we call this instruction set. If you don't know lah, the NEG, what the NEG do, okay, you go to the instruction set, find the NEG. Where is my NEG? Okay, so this one here. Okay, 2 complements, and this is the operation 0, 0 minus RD. Okay, you simply press the calculator, 0, 0 minus with your R20. Okay, the current value of R20 is E6. Okay, then you get F1A. Okay, just take the lower byte, which is the value is 1A. Okay, the rest of the value F, you just ignore them. Okay, then number 4, instruction number 4 is CBR R2150. Okay, so CBR, what does CBR do? Okay, so by looking at this one here, okay, so the CBR, okay, so this is the CBR. You're going to clear bit in a register. So this is the operation. Okay, you're going to end your R21 with a value which is FF minus with K. Okay, so FF minus with 15. Okay, first you need to subtract FF minus with 50 here, and then after that you end with your R21. Okay, press calculator, FF minus 50, you will get AF. Okay, so FF minus, okay, so I put somewhere around here, FF minus 50, you will get AF, and this AF you're going to do logical AND with R21. So R21 is FD. Okay, so this is, no, sorry, not FD, 55. Okay, we already get a new value here, 55. So this is a R21, okay, which is a 55. And then you're going to end with AF. So AF is 10101111. You do the logical AND, and then you will get. Okay, so the answer of R21 now changed to 0, 5. Okay, any question up until here? Okay, I assume that all of you are already get the same result. Okay, then we go to instruction 5. Okay, MULS R20 R21. Okay, so what is this S stand for? Okay, you're going to multiply 2 signed number. Okay, what is the value? R20, 1A, and R21, which is 05. Okay, how you know that this is a signed number or positive number or negative number? Okay, you need to change first lah. Okay, you need to change this hexadecimal to binary and then look at bit 7. Okay, if the bit 7 is 1, then you need to do the second complement. If not, you just get the value and multiply that. Okay, so 1A is actually 0, 0, 0, 1. 1010, and this is 05 is 0000, 0101. Okay, look at this bit here. Okay, since the bit here is a 0, so you know that this is a positive number. So you just simply multiply 1A multiplied with 05. Okay, press the calculator. 1A darab multiply 05, you will get 0082. Okay, the question here is, okay, what is the value that you're going to put to R0 and R1? Why? Because every time you do the multiplication, the result will be stored inside R1 and R2. Okay, so the answer you get is 0082. So what are you going to do here? Okay, you need to divide them to 2 byte, which is low byte and high byte. Okay, for the lower byte will go to your R0. So this is 82. Higher byte 00 will go to your R1. Okay, so all of you get the same result?
No, doctor, I didn't do that one.
Okay, so how about number 6? What is your answer for the number 6? So this one more straightforward because this is a MUL. You're going to multiply unsigned number. Okay, since it is an unsigned number, so you simply multiply the value of R22 and R23. R22 is 13. R23 is F1. Okay, simply press the calculator and what you will get. Okay, anyone? 1183. Okay, so 1183. Okay, so and what about the last one here? The last instruction. Okay, what is the result?
1183.
Okay, that one is for the line 6. Is it 1183 for the line 6? What about the line 7? Instruction 7. Is it 1183 as well?
No, I think.
Okay. Then what is the result? Okay, go saying that FEE3. Okay, one of your friends saying that is FEE3. Anyone got the others answers? Okay, the different answers from Go. Okay, so now let's look. Let's check the Go's answer here is either is correct or not. Okay, so this is a MULSU. Okay, so you're going to multiply signed and unsigned number. So which one is signed number? Which register is unsigned number? So according to this position here, R23 will become your signed number and R22 is your unsigned number. So you go back to your R23 and R22. So this is your unsigned and this is your signed. Okay, for the unsigned number, you can just simply take the value 13. Okay, or you can simply, because this is a multiplication, okay, why not we change it to what we call here decimal number. So 13 actually equal to 19 in decimal. Okay, and then what about R23? So since this is R23 is a signed number, so you need to check whether this is a positive number or negative number. Okay, how to check is a positive number or negative number? By change it to the binary number and then identify bit 7. Either it's a 0 or 1. Okay, so we change to binary first. 1111 0001. Okay, and then you see here bit 7 is 1. So now you know that, okay, now it is a negative number because bit 7 is 1. So what are you going to do? Can you take the value here? Cannot. Okay, you need to find the real value, which is you need to do this second complement. Okay, get the second complement. So what is the second complement? Okay, how to get the second complement? Okay, traverse from right to the left Okay, so find the first number 1. So this is your first number 1. You copy back the answers and the value, and the rest you just invert in them. Okay, you invert them and you get 0, 0, 0, 0, 0, 1, 1, 1, 1, which is this is 0F in hexa. Okay, and then why don't we change it to what we call here decimal. Okay, so 0F you change to decimal, then you will get negative 15. Okay, why negative 15? Because this one here. Okay, previously we already identified this is a negative number. Okay, so we get the magnitude, the value of that number, which is 15, and then you put the negative, and then after that, what you're going to do? You just multiply with 19. Okay, so negative 15 multiplied with 90, you will get negative 285. 285, change it to hexadecimal, then you will get F, 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 E, E, 3. Okay? Okay, you can, okay, you just press your calculator here. Okay, negative 90 multiplied with negative 15. Okay, you get minus 285 and change back to hexadecimal, you get FEE3. Okay, so now you see here, this is only 16-bit. Okay, but now you produce a 32-bit number. So what you're going to do, you need to divide them, okay, into bytes. Okay, then what you're going to do, okay, we just take the lower byte here, okay, which is FF go to your R1 and E3 go to your R0. So the ghost answer is correct. Okay, any question up until here? So we are already finished module 6 and module 5. Okay, next week we continue with module 7. Ada soalan tak? If no question, then